First up, we're going to find the extreme values of the function f of x equals 6x divided by x squared plus 4 on the interval from 0 to 6. The process is entirely the same. We first need to find the critical values. Let's find those critical values. So, in other words, we need to solve the equation f prime of x equals 0. That's the first step. Okay, to solve that equation, we first need to compute the derivative of that function there, 6x over x squared plus 4. That's a fraction, so we got to use the quotient rule. Here we go, here's the quotient rule. The derivative of the top, the derivative of 6x, that's just 6. And then we multiply the derivative of the top times the bottom. And then we subtract off the top, not the derivative of the top, but just the top function, 6x, multiplied by the derivative of the bottom. Derivative of the bottom, derivative of x squared plus 4, that's 2x. And that all goes over the bottom squared. That's the derivative of f. Looks like we can simplify a bit. Let's do so. So I'll multiply through. We get 6x squared plus 24. And then here we have minus 6 times 2 is 12. And there's 2 x's there, so it's 12x squared. We can multiply out the x squared plus 4 squared, but there's no need to. Let's just leave it that way for now. Okay, well 6x squared minus 12x squared, that gives us minus 6x squared. So we have minus 6x squared plus 24 over x squared plus 4 squared. That's the derivative. Okay, we need to figure out when that's equal to 0. So let's set that derivative function equal to 0 and then solve for x. Here we go. All right, first of all, the derivative here, it's a fraction, but the denominator of that fraction is irrelevant. Okay. Because this fraction is equal to 0, we can multiply both sides of the equation by that denominator, x squared plus 4 squared. We end up getting minus 6x squared plus 24 equals 0. And that's fantastic. That's a much easier thing to solve than anything involving this x squared plus 4 squared business. So if we add 6x squared to both sides, we end up getting 24 equals 6x squared, moving it over to the right-hand side. And now let's divide both sides of the equation by 6. We get that 4 is equal to x squared. And so now we just need to find the x values whose square is 4. Well, that's minus 2 and 2. That's the square root of 4 and the opposite of the square root of 4. Those are the two x values, which is square root of 4. That's great. These are the critical values. Those are the x values where the derivative is 0, where the tangent line is horizontal. Okay, the next step in the process is to evaluate the function. I'll write down the formula again for you. It was 6x over x squared plus 4. We need to evaluate that function first at those critical values that we just found, and then at the endpoints of the interval. So let's first do the critical values. What happens if you plug in... Oh wait, there's an important point here. We need to evaluate this function, but only at the x values that are in the interval that we're considering. We're only considering the interval from 0 to 6. That was given to us in the problem. So we can actually save a little bit of work here. We don't need to consider this minus 2. It is a critical value, but there's no need to worry about it. It's not in this interval from 0 to 6. It's not under consideration. We're only accepting x values in between 0 and 6 in this problem. So the only critical value that we need to evaluate the function at, after we've restricted attention to that interval, is 2. All right, what happens if you plug in x equals 2? here we go. We have 6 times 2, that's 12, divided by 2 squared plus 4, and that's 8. So the output of the function is 12 over 8, and dividing out, canceling a factor of 4 from top and bottom, we get 3 over 2. That's the output of the function at the critical value 2. Groovy. We also need to evaluate the function at the endpoints of the interval. That was the interval 0 to 6. The maximum or minimum might happen at those endpoints of the interval. Let's see what happens if we plug in 0. Well, here in the formula there's a 6x on top. That x is going to become a 0. So we'll just get 0. That's easy. And if you plug in 6, you get 6 times 6 over 6 squared plus 4. Well, that's 36 over 40. And so canceling the common factor of 4, we get 9/10 as the output at 6. The final step is to compare. Which of these numbers that we've gotten as outputs is the smallest? Which is the biggest? Well, the numbers were the output at the critical value 2, that was 3/2, 0, and 9/10. Which is bigger? Notice that 9/10, there it is, 9/10 here, that's less than 1, right? 3/2, that's bigger than 1. So 3/2, that's the biggest number. That's the biggest output that we see there. So the maximum value of the function is 3/2, and this occurs at the x value, the input 2. What's the minimum value, the smallest number that we see there? Well, we have 3/2, 0, and 9/10. 0 is the smallest, so that's the minimum value, and that occurs at x equals 0. So those are the global max and min values of this function. We can see that through this process even if we don't have a picture of the graph. Even without the graph, we can find the global extrema. Here we see on Desmos a graph of the function that we were just finding the max and min of. That was 6x over x squared plus 4. And here we see the two critical values, the points where the derivative is 0 on the graph. Again, they correspond to a little valley or a little peak. Those are the points where the tangent line is horizontal. But remember, we didn't consider -2 in the end because we were restricting attention just to the interval from 0 to 6. We only care about those values. So I can make Desmos show that in the following way. If you type less than and then the equals sign, Desmos will give you a less than or equal. Let's do that this time so that those endpoints are included. Okay, great. So that's the piece of the graph in between 0 to 6. That's the graph over the interval under consideration. There we have the maximum that we found. That's 3/2, aka 1.5, occurring at 2. And the minimum value of 0 occurring there at the left.
Hey, leader of the free world, answer this!
In the next example, we're going to find the maximum and minimum values of the function g of t equals cosine of 2t plus t on the interval 0 to 4. So we only consider t values in between 0 and 4. The process is the same as before. The first step is to find the critical values. That just means the x values where the derivative is 0. In other words, we need to solve the equation g prime of t equals 0. That'll tell us the critical values. All right, what's the derivative of this function? Well, cosine of 2t, it has 2t there as an inside function. And then cosine is the outside function. We got to use the chain rule. So we have the derivative of cosine, that's minus sine, evaluated at the inside function, but then multiplied by the derivative of the inside function. Derivative of 2t, that's just 2. So that's the derivative of cosine of 2t. What's the derivative of t? That's just 1. Taking the derivative with respect to t there. Okay, let's just move that 2 out front. I like to put my constants out front. It just makes me feel a little bit better. So that's the derivative rewritten. And now to find the critical values, we've got to set it equal to 0, and then solve for t. Here we go. Well, if we add 2 sine of 2t to both sides, we'll get that 1 is equal to 2 sine of 2t. And then dividing by 2, we get that sine of 2t is equal to 1/2. Okay, now we have to remember, where does the sine function take on the value 1/2? Got to remember our unit circle. Remember, the sine is the y-coordinate on the unit circle. So we're looking for those angles where sine, the y-coordinate, the height, is equal to 1/2. That occurs at these 2 points. I'll remind you that the x-coordinate is √3/2. That would be the cosine. The y value is 1/2. And then over here it's the same, but the x-coordinate is negative. The y value is still 1/2. What are the angles where this occurs? That first angle there, that's pi/6. And the second angle here, that's almost halfway around. It's almost to pi. It's 5π/6. So those are our angles where sine of 2t is equal to 1/2. So by looking at the unit circle, we see that this equation is satisfied when 2t is equal to pi/6 or 5π/6. But wait, there's another possibility, right? Because we could consider the angle where we go all the way around the unit circle and we come back to this point. That's a valid angle. It's more than 2π, but it's a valid angle. In fact, it's exactly 2π plus pi/6. Okay, and that is 13π/6. Similarly, if we do 2π and then we add on 5π/6, what would we get? We would get 17π/6. It's almost all the way around to 3π/6, which is 1.5 times around the unit circle. And then the list goes on. Now, we don't need to write down all of those angles. In fact, it would take us forever to do so. It's an infinite list. And the reason for that is that in the next step, when we actually solve for t, right, these were just the angles where the sine was 1/2. That was just 2t we were solving for. If we divide by 2 in this list, what we need to consider is which of these angles are in the interval that we're concerned with in this problem. Oh, whoops, 5π/6, I forgot to divide by 2. That should be 12 there. Sorry, that's a 12. Okay, so which of these values for t, these critical values that we found, which of them are in the interval 0 to 4? All right, so let's see here. Pi, it's a little bit more than 3. So this is like a little bit more than 39/12. That's, a bit larger than 3. That's still in the interval. But this number, 17π/12, if you put it in a calculator, you'll see that 17 times pi, that's larger than 51. So this is certainly larger than 48/12, which would be 4. So this is larger than 4. It's not in the interval, whereas these 3 are in the interval. Notice that since the interval starts at 0, we don't need to consider the negative t values, right? We could have considered the negative angles whose sine is equal to 1/2. Since that number is bigger than 4, it's not in the interval under consideration. So that value and all the ones bigger than it, we don't need to consider. We only need to consider those first 3 critical values. In the next step, we're going to evaluate the function at those critical values that we found, as well as at the endpoints. So let's do it. Let's evaluate the function. First of all, if we evaluate the function at those critical values, what do we get? There's 3 of them that we need to plug into the function. So what's g of pi/12? Well, let's see, that would be cosine of 2 times pi over 12 plus pi over 12. It looks horrible, but it's not so bad, right? You can cancel out a factor of 2, so this is just pi over 6. And you know, we already talked about cosine of pi over 6. Cosine of pi over 6, this angle, that's the x-coordinate here, that's root 3 over 2. So the cosine of pi over 6 is root 3 over 2. And so the output that we get is root 3 over 2 plus pi over 12. Alright, we're going to need to compare this to some other numbers, so this really isn't good enough. In this case, we should find a decimal representation of this output. If you plug it into a calculator, you'll get 1.127825 and so on. It's an infinite decimal that goes on, but that'll be good enough for our purposes. Okay, what are the other critical values? We just evaluated at pi over 12. The next one on the list is 5 pi over 12. So in this case, we'll be taking cosine of 2 times 5 pi over 12 plus 5 pi over 12. What's that? Well, it's a similar calculation. If we cancel the 2 from top and bottom here inside the cosine, we're going to be left with 6. So we're looking at cosine of 5 pi over 6. And we also already discussed that. Remember here at 5 pi over 6, it's the exact same values except the x-coordinate is negative. Cosine is the x-coordinate, so the cosine of 5 pi over 6 is minus root 3 over 2. So this output is minus root 3 over 2 plus 5 pi over 12. And if you plug that into a calculator, you'll get 0.442972 ... Goes on and on forever. That's good enough. And there's one more critical value to plug in. And that was the third one, 13 pi over 12. We have cosine of 2 times 13 pi over 12 plus 13 pi over 12. What's that? Well, canceling the 2. Again, we have 13 pi over 6. Remember, where did that 13 pi over 6 come from? We found that one by going around the circle a full 2 pi and then one more pi over 6. That's 2 pi plus pi over 6. So we're back here at this angle after a full revolution. The x-coordinate is again root 3 over 2. So this output of the function is root 3 over 2 plus 13 pi over 12. If you plug that into a calculator, you'll get 4.269417 and so on. Okay, so we've evaluated the function at the 3 critical values that lie in the interval 0 to 4. That's the interval we're considering. We also need to evaluate the function at the endpoints of the interval. So I'll do that down here, and then leave the other sheet of paper up there for reference. We're going to need those numbers. So let's now evaluate the function at the endpoints of this interval. That's the interval from 0 to 4. So g of 0, that would be cosine of 2 times 0 plus 0. 2 times 0, that's just 0. What's the cosine of 0? Well, that's the point on the x-axis, right? On the unit circle, this point right here where the angles start, that's the angle 0. The x-coordinate there is 1. So cosine of 0, that's just 1. 1 plus 0, that's just 1. So the output of the function at 0 is 1. What about at 4? Well, that would be cosine of 2 times 4 plus 4. And now there's really cosine of 8. There's not much we can do about that. Remember, we're working in radians. I mean, cosine of 8 radians, the only way you can deal with that is plugging it into a calculator. And if you do so, you'll get 3.854. That's good enough. Why is it good enough? Because in this final step, we got to compare all these outputs and see which is biggest, which is smallest. Here's our list of outputs. All right, there's the 3 outputs at the critical values. There they are. Then there's the output 1 and the output 3.854. Which is biggest, which is smallest? Let's see, it looks like this is the largest. It's bigger than 4. Nothing else is bigger than 4. That's going to be the maximum value. What's the smallest of these numbers? Up here this is 1 point something. And this is less than 1. That's just 0 point something. That's going to be the minimum. So those are our maximum and minimum values of this function. In this case, the value of the function at the endpoints of the interval was irrelevant. It didn't achieve a maximum or minimum there. So let's record the answer. The maximum value is, I'll write it first in terms of its honest answer, it was root 3 over 2 plus 13 pi over 12. That was in decimal form. Something like that. And that occurred at the t-value 13 pi over 12. And the minimum value on this entire interval was minus root 3 over 2 plus 5 pi over 12. That was the one that was 0.442972 and so on. And that occurred at t equals 5 pi over 12. So that's a complete answer. That's the largest and smallest value that this function obtains on the interval from 0 to 4. Here we have a graph of this function g of t. We were using cosine of 2t plus t. I've typed into Desmos using x. Desmos likes x as the name of the input variable. That's fine. And check it out. Here on the graph we can find these values of t where the derivative is 0. These are the critical values that we found. Right? Pi over 12, 5 pi over 12, 13 pi over 12, 17 pi over 12. But wait, 17 pi over 12, we figured out that was not under consideration because it's bigger than 4. Yeah, indeed, it's to the right of this line, x equals 4. So here, this kind of oscillating but growing function, if we want to find its maximum values on that interval, again on Desmos we can just restrict to x values that are in between 0 and 4, using that notation I've just typed in there, and then it shows us the bit of the graph that we care about. And we find the maximum value at 13 pi over 12, and the minimum value at 5 pi over 12 that we found by hand. That was 4.269 thereabouts, and 0.443 thereabouts. Fantastic.
Who's going to win the next award? Really? Stay tuned for the 42nd annual Emmys with the Golden Girls. Just a minute. What? Well, you should have thought of that before we sat down.